Polar coordinates. Before diving into polar coordinates, let's review the Cartesian coordinate system. Given a Euclidean xy plane, using rectangular or Cartesian coordinates x, y to graph functions y equals f of x or other equations like circles is only one way of navigating through the xy plane. So, for example, if we have a coordinate point x, y, recall that this means to move x units to the right if the x value is positive or left if the x value is negative, then move y units up if the y value is positive or down if the y value is negative. So here is an xy plane, and to graph the coordinate point -3, 5, from the origin we move 3 units left and 5 units up. Now let's explore the polar coordinate system. Some curves can be more easily expressed using points of the form r, theta instead of x, y, where r is the directed distance from the pole and theta is the angle with initial side on the polar axis. Let's explore these new terms. So here I have the intersection of two planes, and instead of labeling them the x-axis and the y-axis with this intersection being the origin, we're going to call the intersection the pole when we're talking about the polar coordinate system, and what would normally be the positive x-axis we're going to call the polar axis. In order to graph polar coordinates of the form r, theta, we actually go to the angle first, and then we address the directed distance r from the pole. For example, here I have the polar coordinate 2, pi over 4. So notice that the coordinate point is an angle measure of pi over 4 away from the polar axis. So here, this is a measurement of pi over 4. And then the value 2 tells me how far away to go from the pole. And because I am a positive 2, I'm going to go towards the angle pi over 4. That's what we mean by directed distance. So in other words, I can count how far away I am from the pole by using these rings. So you'll usually find that the polar coordinate system looks like this, where only the polar axis is labeled, and we have these rings to help guide us a particular distance away from the pole. So now, just for practice, let's go ahead and see what the polar coordinate -2 pi over 4 would look like. So we would go to the angle pi over 4, and instead of going towards pi over 4, because we have a negative directed distance, I would go 2 units away from the pole. So down here, I would label my coordinate point. This is -2, but still positive pi over 4. So first we would have went to the angle pi over 4, and then from the pole we would travel 2 units away from the pole to establish my directed distance of -2. In this example, we're going to go ahead and continue to graph some polar coordinates. Here is our blank polar coordinate system, and I'm going to go ahead and label the polar axis. And I'm going to label just the angles for now in quadrant 1. So we have 0, we have pi over 6, we have pi over 3, and we have pi over 2. So let's go ahead and graph the following polar coordinates. We have A is 2, pi over 6. So what we do is we first go to the angle. So here's the angle pi over 6. And since the directed distance is +2, I go 2 units towards pi over 6, landing me right here as my coordinate point that I'm going to go ahead and label A. Now let's go ahead and try to graph B. Here I have 3, negative pi over 2. So negative pi over 2 is the angle, and a negative angle means that I go in a clockwise direction. So negative pi over 2 is down here, And then I go ahead and look at the directed distance. Since the directed distance is positive, I'm going to go from the pole 3 units towards negative pi over 2. So that's going to go ahead and bring me down here, and I'll label this point B. Let's go ahead and move on to C. We have negative 2 comma pi over 3. So here we're going to start at the angle pi over 3. So here it is over here in quadrant 1. However, our directed distance is negative 2. So instead of going 2 units, going out these like 2 rings towards pi over 3, I'm going to go in the exact opposite direction. So I'm going to go ahead and go 2 units away from pi over 3, landing me right here, and I'm going to label that my point C. So if I'm directly across from pi over 3, I'm still going to have a reference angle of pi over 3. So this angle down here is actually 4 pi over 3. Let's go ahead and try part D. We have negative 4 comma 3 pi over 4. So 3 pi over 4 isn't labeled for us. This is going to be an angle in quadrant 2, and it's actually going to be halfway between pi over 2 and pi, so halfway between a half and 1 pi, and so we can see that isn't actually drawn here as one of my line angles, but that's okay. I can still go ahead and graph this point. So I want to make sure that I'm halfway between, again, this is 2 pi over 3 and 5 pi over 6, but I actually have a negative directed distance. So instead of going towards 3 pi over 4, so I'll go ahead and draw a line here. This would be positive 3 pi over 4. I'm going to go in the exact opposite direction, which would actually be going towards 7 pi over 4, because my directed distance is negative. So I'm going to go ahead and go 1, 2, 3, 4. Units towards 7 pi over 4 away from 3 pi over 4. And then finally, E, I have negative 4 and then negative pi over 3. So here, we're going to go ahead and go to negative pi over 3, which remember is a clockwise angle. So that's going to be down here. I have negative pi over 3. And whoops, I didn't label this. This is D. So here I have negative pi over 3, but because I have a negative directed distance, instead of going towards negative pi over 3 from the pole, I'm going to go directly away from negative pi over 3. So that's going to lead me towards 2 pi over 3, and I'm going to go 4 units. So 1, 2, 3, 4 rings out, and label that E. In this example, we want to show how to convert from polar coordinates, so 2, 5 pi over 6, and r theta, to a rectangular coordinate, the x, y type of coordinate. So we have a conversion factor here. So if we start with an r and a theta, then to get to an x, y, we're going to have our cosine theta multiplied together as our x value, and our sine theta multiplied together as our y value. And those are coming from our definitions of sine and cosine. Cosine of theta is an x value over the radius, and sine theta is the y value over the radius. So note there can only be one answer. So there's only going to be one answer that comes out here, one rectangular coordinate point, x, y. So let's go ahead and find that. Our x, y is going to be 2 times cosine of 5 pi over 6, and 2 times sine of 5 pi over 6. So now we're going to go ahead and evaluate the trig functions in here. So I have 2 times cosine of 5 pi over 6 would be a negative radical 3 over 2. And then I have 2 times sine of 5 pi over 6. That's going to be a positive 1/2. So notice that the 2's in each of them are going to cancel out. So my coordinate point is going to be negative the square root of 3, 1. And we can just do a brief check just to make sure that we're in the right quadrant. So graphing 5 pi over 6, Well, what that would mean is going to the angle 5 pi over 6. So it's right about here. I'd go 2 units towards 5 pi over 6, so just a rough estimate of going 2 units towards this 5 pi over 6 angle. And does that match up with this being an xy coordinate? Well, yeah, because I'd go negative, so I'm over here to the left, and then up 1, so I am in quadrant 2. In this example, we're going to go the other way around. We're going to convert negative 3, 3, a rectangular coordinate, to polar coordinates. But this can actually be done in more than one way. So we're going to represent the coordinate with both r as a positive value and r as a negative value. Let's look at the conversion factors. So to go from rectangular to polar, from xy to r theta, we have to do a little bit of work and a little bit of critical thinking here. So the r value is plus or minus the square root of x squared plus y squared. So we're going to have to choose whether r is positive or negative depending on our angle. So to find our angle, we're going to use tangent inverse of y over x. So to decide the positive or negative, for r, it's based on the quadrant of the coordinate point. And when we find this theta star, that's only going to be the reference angle. So we are going to have to do some thinking about where this point is and how to represent it as a polar coordinate, because polar coordinates can be represented in infinitely many ways. So here, let's go ahead and get started. So we're going to convert negative 3, 3 to polar coordinates. So I'm actually going to start by just plotting negative 3, 3. So I'm just going to do a quick little plot of negative 3, 3. So that's going to lead me over here to quadrant 2. So I'm trying to find a way to represent this particular coordinate point as a polar coordinate in two different ways, with a positive directed distance and a negative directed distance. And you might be thinking, I can actually just figure out what that is by looking at it. And I'm not going to disagree with you, but I want to make sure we can do it for any coordinate point. So we are going to follow this set of formulas over here. So to find r, we're going to go ahead and do r is plus or minus the square root of negative 3 squared plus positive 3 squared. So we're going to have plus or minus the square root of 18, which is plus or minus 3 radical 2. So I'm going to just hold off on that for a second. I'm going to leave those two values. And now I'm going to go ahead and attempt to find what I'm calling theta star, the reference angle. So we're going to do tangent inverse of y over x. So I'm going to go ahead and do theta star is tangent inverse of the y value 3 over the x value negative 3, or tangent inverse of negative 1. Now, tangent inverse of negative 1 is exactly negative 45 degrees if I use degrees, or negative pi over 4 if I use radians. So negative 45 degrees is actually down here in quadrant 4, because tan inverse is restricted to quadrant 1 or 4. So here, down here, is my negative 45 degrees. So now let's think about how we're going to use this angle and the correct directed distance to navigate someone to this coordinate point. So let's go ahead and start by using negative 45 degrees. If I am going to use negative 45 degrees, or negative pi over 4, then instead of using a positive directed distance, because that would take me down here to quadrant 4, I have to use the negative directed distance because I want to navigate myself up here to quadrant 2. So I have to have negative 3 radical 2 as my polar coordinate, and that's with r less than 0. Well, if I want to use r greater than 0, if I want to use the positive directed distance, 3 radical 2, then I'm actually going to need to know, well, what is this angle here that's directly across from negative 45 degrees? Well, in degrees, that's 135 degrees. So basically this was our reference angle. If I make it positive, this angle here is 45. So I did like 180 minus 45 degrees. That got me to 135 degrees. Or again, in radians, that would be 3 pi over 4. So I'll stick with degrees and write 135 degrees. Now let's move on to an example where instead of converting coordinate points, we're going to convert equations. So convert the following equation from rectangular to polar and graph it. So here we have y equals x minus 3, which recall is a line in slope-intercept form, y equals mx plus b. So here I'm going to go ahead and convert this to polar. And to do that, I want all r's and thetas in my equation. So we just said that y was equal to r sine theta. So I'm making the replacement. Y is r sine theta equals x. Well, that's r cosine theta minus 3. So here I have turned my rectangular equation with x's and y's into a polar equation. What we typically want, though, if possible, is we want to solve for r. Just like on a rectangular equation, we often want to solve for the variable y. So here that is going to be possible. I can subtract the r cosine theta to the other side in order to factor out the r. And then I'm left with sine theta minus cosine theta multiplied to r. So I can divide by that quantity. So r is negative 3 over sine theta minus cosine theta. So it turns out that this equation in rectangular is equivalent to this equation here in polar. So let's go ahead and graph it. A line is easily graphed from rectangular. We can go ahead and graph the y-intercept as negative 3, and then the slope is positive 1. So I'm going to have my slope positive 1 means it'll intersect over here. So this is my line, y equals x minus 3. So on this one, I would definitely say it's probably easier to graph this from its rectangular form than its polar form. Let's go ahead and do this one more time, convert from rectangular to polar. Here we have x squared plus y squared equals 4. And as a rectangular equation, we recognize this to be a circle in standard form. So standard form of a circle is x minus h squared plus y minus k squared equals r squared. So this is a circle centered at 0, 0 with a radius of 2. Let's convert it to polar and see how it looks. So here we're going to let x be r cosine theta, and we're going to square that. Y is r sine theta, and we'll square that, equals 4. So we end up with r squared cosine squared theta plus r squared sine squared theta is equal to 4. We can square each part because these are multiplied, not added. And then here I have an r squared in common in both that I can factor out. So r squared is multiplied by cosine squared theta plus sine squared theta, and that's equal to 4. So now notice we have cosine squared theta plus sine squared theta, which is our Pythagorean identity, so this whole thing equals 1. So we're simply left with r squared is equal to 4, or r is equal to plus or minus 2. So it actually became two different polar equations, r equals positive 2 and r equals negative 2. And both of those are going to represent this circle centered at the origin with a radius of 2. So let's go ahead and graph it. So here we'll go ahead and graph our circle centered at the origin with a radius of 2. So I would actually say that the polar equation on this one is an easier equation. R equals positive 2. That just means that the directed distance from the pole is always 2. So we're looking at every single point that's 2 units away from the pole. well, that's just forms a circle. And if we're negative 2 units from the pole, we're just going the opposite direction of every angle, we're still all those same coordinate points that form a circle. So I think on this one, absolutely, the polar equation is a lot simpler than the rectangular equation. In this example, we want to write as a rectangular equation and then graph it. So here we're starting with a polar equation, r equals 4 sine theta. So what we want to do is we want to be able to use our formulas that involve r, theta, x, and y. So just as a reminder, I had x is equal to r cosine theta, I had y is equal to r sine theta, I had x squared plus y squared is equal to r squared, and we also had that tangent theta is equal to y over x. So these are all of our equations that relate r, theta, x, and y, and so we're trying to establish how are we going to manipulate this so that we can use these equations. On this example, what I'm going to do is multiply each side by r to give us r squared on the left and 4r sine theta on the right. Because now r squared is equal to x squared plus y squared, and on the right hand side I have 4 times r sine theta. Well, r sine theta is just y, so I have equals 4y. And so now here I want to think about what this equation looks like. So this is a conic section, and I'm going to go ahead and subtract the 4y to the other side for a second. So I have x squared plus y squared minus 4y is equal to 0. And in order to be able to recognize what this is, I'm going to go ahead and complete the square on the y squared minus 4y part. So I have x squared plus y squared minus 4y plus 4. So completing the square here, if I take the negative 4 divided by 2, I get negative 2. Negative 2 squared is 4. But if I add 4 to one side of the equation, I have to add 4 to the other side of the equation. And now these three terms are a perfect square. That's why I completed the square. So I have x squared plus y minus 2 quantity squared equals 4, which is 2 squared. So now, hopefully it's easier to see and recognize what we actually have here is we have a circle. So we have a circle that's centered at 0, 2. So the value next to x is 0, and here I have y minus 2, so 0, 2. And then the radius is 2, right? 2 squared. So here I have a circle, 0, 2 is its center, and its radius is 2. So we'll go ahead and graph that, right? Graph it. So the center being 0, 2 is going to be up here. And if the radius is 2, I'm going to do my best, and hopefully it straightens it out, makes it nice for me. All right, not too bad. So here I have my circle with center 0, 2 and a radius of 2. So it looked like x squared plus y minus 2 squared equals 4. As opposed to, if I use the polar equation, I have r equals 4 sine theta. So I want us to think about that for a brief second before moving on to see if we can recognize why it is 4 sine theta here, how we can make a connection to help us remember in the future that 4 sine theta graphs a circle that's up here on the positive y-axis. Well, notice that the diameter here is 4, and sine theta, well, sine corresponds to which variable? Y. So notice that the circle is on the positive y-axis here, and that's because it was a positive 4. So graphing r equals 4 sine theta actually didn't require us to do the whole convert it to a rectangular work that we just did. We could just recognize this general form, this like a sine theta, where the a is the diameter, and because it's sine theta and it's positive, it's going to be up on the positive part of the x-axis. So for example, just to briefly show, let's say I have r equals negative 4 sine theta. Well, because it's sine, it's going to be along the y-axis, but because it's negative, it's going to be below the y-axis. And it's still going to have that radius, I missed a little bit, but it's still going to have, that diameter of 4. So this circle down here is -4 sine theta. And in case you're wondering, if it happens to be, let's say, 4 cosine theta, then it's going to exist on the positive x-axis, and -4 cosine theta will exist on the negative x-axis with the diameter of 4. And in this example, again, we want to express it as a rectangular equation and then graph it. So we have theta is equal to pi over 4. So if we want to include our formulas from earlier, here we have our relationships between x, y, r, and theta. So here, what I'm going to do is I'm going to go ahead and take tangent of both sides of this equation to involve this over here, tangent theta equals y over x property. So I have, if I take tangent theta of both sides, I have tangent of pi over 4, which is 1, and tangent theta is y over x. So if I want to solve for y, I'm just going to multiply by x. So it turns out that theta equals pi over 4. This is a polar equation. It has theta in it. That's the same as the line y equals x. So we're just talking about the line that passes through the origin with a slope of 1. And notice what angle that line falls on. It falls on the line, or on the angle, pi over 4. And since we can have positive r's and negative r's, it's the entire line, not just in the first quadrant, but also on the opposite side in the third quadrant. Now let's strictly move on to graphing polar equations. And we don't want to do this by having to write it as a rectangular equation. So what we can do to graph polar equations is we can graph them by inputting angles and finding outputs that are directed distances, similar to how we would plug in x's and get out y's. So in other words, if we wanted to graph, let's say r equals 3, we would plug in different angles, input angles, so thetas, and see what happens to r. Well, on this first straightforward example, since I have just the constant r equals 3, it doesn't matter what angle I plug in, 0, pi over 2, pi, or 3 pi over 2, I'm going to constantly get out the directed distance of positive 3. So that leaves me with a bunch of coordinate points, just like we would plot x comma y. So our coordinate points are r thetas. So 3, 0, 3 pi over 2, 3 pi, and 3 pi over 2. So we're plotting the quadrantal angles, and that's a good place to start. It's kind of like when you graph a line and you plug in -2, -1, 0, 1, and 2. So a good place to start if we're going to plot points, we're going to plug in these quadrantal angles. So now let's actually graph these points. So 3, 0, remember 0 is the angle 0, and we're going 3 units towards 0. So I'm going to end up right here, so labeling the polar axis. So this is one coordinate point. 3 pi over 2 is up here. I go 3 units towards pi over 2. Over here at pi, so I have 3 units towards pi. And then 3 pi over 2 is down here. And if I go 3 units towards 3 pi over 2, I have this coordinate point. So hopefully we can see that this is going to form a circle. So if I connect the points here, I have just a circle with radius 3. And again, that should make sense because I'm always a directed distance of 3 away from the pole. In this example, we're going to graph the following regions based on our previous examples and our understanding of these polar coordinates and polar values. So here, this region, this says that the r values are always between 1 and 3. So here we have 1, 2, 3 labeled on our polar axis, so we're always going to be between 1 and 3 in our r values. And then our angles, we're always going to be between 0 and pi over 2. So 0 is here and pi over 2 is here. So we're graphing an entire region right now. So that region is going to extend from 0 to pi over 2, but be bounded between 1 and 3. And since they're all less than or equal to, these are all going to be solid lines. Oops, that got a little messy. So they're all going to be solid lines here, and we're talking about the region, so I'm going to go ahead and shade in this portion here. So we're graphing inequalities right now that deal with our directed distance and our angle. And then over here, let's just think about what happens if we're restricting the angle theta to be between 2 pi over 3 and 5 pi over 6. So let's recall both of those angles would be over here in quadrant 2. So I have, this is 2 pi over 3 and this is 5 pi over 6. So we're talking about our angle being always between, less than or equal to, so I'm drawing them as solid lines, between 2 pi over 3 and 5 pi over 6. So this portion right here would be part of the region I'm talking about, but because there's no restriction on r at all here, remember that our r's, our directed distances, could also take us directly away from these values in here. So that means that the little pizza slice on the opposite side in quadrant 4 would also be part of this region. In this example, we want to graph the polar curve r equals 1 minus sine theta. And we'll start by graphing points. So we have to input angles, and we'll get out directed distances. So I have a couple of angles here, and if we substitute them in, if I substitute in 0, sine of 0 is 0, so the output for r is 1. If I plug in pi over 6, sine of pi over 6 is 1/2. So 1 minus 1/2 is 1/2. And if I plug in pi over 3, I'm going to get 1 of sine of pi over 3, which is 1 minus radical 3 over 2. And so that's not a value I would want to graph. I want to be more specific, so let's approximate it. That's 0.133. And if I plug in pi over 2, sine of pi over 2 is 1, so 1 minus 1 is 0. And we can sort of continue on. I have a couple other angles here, and I'm going to give you the values. We get that 0.133 approximate value again at 2 pi over 3. We get 1/2 at 5 pi over 6. At pi we get 1, and at 3 pi over 2 we get 2. So we plugged in angles, we got out directed distances, and from there we have a set of points. Now the points, remember, are of the form r comma theta, so the directed distance goes first. So these coordinate points are 1, 0, 1/2, pi over 6, that 0.133, pi over 3. So the angle always goes second, and so on. All right, so now let's plot these polar coordinate points. Now this here is the polar axis, so we'll label this 1, 2, and 3, and these angles are pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, pi, 7 pi over 6, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 11 pi over 6. So the pi over 4 angles are not included here. At least they're not marked, right? So here we would go to the angle first. The angle is 0, right? And we would go 1 unit towards 0. So that first point is right here. For this next point, I'd go find the angle pi over 6, and I'm going to go 1/2 a unit towards pi over 6. So that's going to be about halfway there. And then at the angle pi over 3 for the next point, I'm barely going to go out to 0.133. So I'm just going to go out a little bit to 0.133. And at pi over 2, I'm going to stay at the pole. So I'm going to have a point right there at the origin. And at 2 pi over 3, I'm going to have that 0.133 again. At 5 pi over 6, I'm going to have 1/2 as the point, or the directed distance, excuse me. And at pi, I'm going to have 1. So I'm going to go 1 unit towards pi, right? And from there, I substituted in pi. Then the next value I have listed is 3 pi over 2, the next angle, and I would go 2 units towards 3 pi over 2, so that's going to take me down here. So I didn't, although I could have, substituted in these other angles, but here's what I'm going to go ahead and do. I'm going to start to connect these points. So I have this little curve here, and this curve here, and then what's going to happen is it's going to widen out. It's hard to draw this freehand, but it's going to sort of widen out here as it gets to that 3 pi over 2 point. And then there is symmetry, so it's going to look the same on the other side. Tried my best there. So we can plot points just like we can with an equation in x and y. Now, if you found that option a little bit tedious, there is another way. So we are going to graph the equation r equals 1 minus sine theta on a theta r plane, and then we're going to use that to sketch the polar graph. So what do I mean by that? So here's kind of how I like to think about it. Let's pretend that we're back in x's and y's for a second. So let's pretend we're graphing y equals 1 minus sine x. So think about it as the x and the y axis. All right, so 1 minus sine x should be a pretty nice graph for us to create relatively quickly on one period, on a period of 0 to 2 pi. So I'm going to go ahead and label my tick marks there. All the quadrantal angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi. And let's just kind of remember the phases of the graph. So I'm going to sketch them and then erase them, but just to remind you. So sine x originally just starts at the origin, right? And it's going to go up to the amplitude of 1, back down to pi 0, then to negative of the amplitude, -1, and then back to 2 pi. So my general sine wave, right, is going to look like this. This sine wave, though, is reflected because of the negative in front of it, right? So then it's actually going to look like this, a reflection over the x-axis, and we can't forget about this 1, which is going to move everything up 1 unit. So the final graph here, if everything moves up 1 unit, basically means like the x-axis shifts up. So it's going to start at 1 on the y-axis, and then it's going to go down to pi over 2, 0, back up to pi 1, then 3 pi over 2, 2, and then 2 pi 1. So this is the graph of y equals 1 minus sine x, but it's the graph of r equals 1 minus sine theta on what we call a theta r plane. Right, so theta and r. So what we can do is use this graph to help us sort of unroll this information onto my polar coordinate axis. So remember, this is the polar axis. We'll label it 0, 1, 2, 3, and then we'll label our values here again. Whoops. So here's how we want to start this process. We want to look at this horizontal axis, which represents theta, the angles, And we want to analyze what's happening to the outputs, the R values, which are directed distances. So let's take it sort of one quadrant at a time here. So between 0 and pi over 2, that's what's going to tell me what's happening in quadrant 1 on my polar graph. Well, if I describe what's happening on this this theta R plane right here, between 0 and pi over 2, these R values are decreasing. So I'm just going to write that down here. R is decreasing from 0 to pi over 2. The R values are starting at 1 and decreasing down to 0. So what I'm going to do is I'm going to come over here to the angle 0 and mark the point 1, because at 0 the directed distance here is 1, but then those directed distances, they get smaller and smaller until I get to pi over 2. So what's happening, right, is that that first directed distance, I'm gonna draw it with some lines, and then I'm going to erase the lines. So the first directed distance from the pole is 1. And then those directed distances started to get smaller, right? So they're getting smaller, which means that they're getting closer and closer to that pole, right? So that's what's happening to the directed distances. Over that first interval from 0 to pi over 2, they're shrinking. So that's why the graph, as we already know because we graphed it already, has that shape that's getting smaller as I curve around from 0 to pi over 2. So these lines, I'm going to erase them now, right? Those are not actually part of the graph. It's really just those outside points, right? And so then we can move on and say, well, what's going on between pi over 2 and pi on this theta R plane? And that's going to tell me what happens in quadrant 2 over here. Well, what's happening to those directed distances is that they are increasing, right? So R is increasing. And R is increasing from 0 to 1. So I start at 0, I start at the pole, and then I'm getting bigger and bigger and bigger and bigger and bigger and bigger all the way to 1. Right? So that's what's happening to those directed distances. They're getting bigger, which is why we have that shape, that symmetrical shape on the other side. So again, I'm going to erase those little lines there. Okay. Now, from pi to 3 pi over 2, what is happening is that R keeps increasing, but R is increasing from 1 all the way to 2. So at 3 pi over 2, the directed distance is 2. So that means I can come down here, I can label that point, and so the radii just keep growing from 1 bigger and bigger and bigger all the way up to 2. So it's like slightly bigger, and then bigger and bigger and bigger, right? So I'm just doing my best here, right? Something like that. So those radii are getting bigger as I move from pi to 3 pi over 2. So now I'm going to kind of go along the edge there, right? And so that continues that next part. And then finally, between 3 pi over 2 and 2 pi, my R values are decreasing from 2 to 1. So they're getting smaller from 2 to 1. So they were all the way at 2, and then they're going to get a little smaller, a little smaller, a little smaller, until I get to that 1. And so I am going to make it, well, I'm going to try to make it symmetrical, but it didn't work out great, right? Okay, I'm going to erase these. So that's another way to sort of work this process. So what we could have done over here to kind of help, R is decreasing you know, from 1 to 0, those Y values. The R values were increasing. They were going from 0 to 1. Here they were going from 1 to 2. And here they were going from 2 back to 1. So, you know, this is really just to help, again, kind of unroll the graph around the angles, right, on the polar coordinate system. Now to conclude, I just want to mention this graph sort of looks like a heart, and it has a special name. It's called a cardioid. And so some of these polar graphs have some special names, and we'll take a look and classify those later. Now this is calculus after all, so let's start talking about the slope of a polar curve. If we can graph a polar curve, we can start to talk about the slopes at different points. to find the slope of a polar equation, r equals f of theta, like the one we just graphed, we can use the parametric equations x equals r cosine theta. And if r is f of theta, this becomes f of theta times cosine theta. And then y is r times sine theta. And again, r gets replaced with f of theta, so f of theta times sine theta. So the parameter here is theta. And when we looked at parametric equations, it was often t, but here the parameter is theta. So to find dy dx, what we are familiar with, right, dy dx as the derivative or the slope, we're going to introduce that parameter by saying this is dy d theta over dx d theta, or d theta of y, d theta of x, right, so doing this quotient here. And if y is f of theta sine theta, then this becomes the derivative of this product. And if x is f of theta cosine theta, then we have the derivative of this product here. And if I'm doing a product, then I need the product rule. So I don't really think this is, worth memorizing. It's really about understanding the parameters. That y, when we think about sine, we should think about the y coordinate. So y is r sine theta, and then x is r cosine theta. But it does create a product because of the fact that r is a function of theta as well. So we have to apply the product rule. All right, so let's do an example. Let's find the slope of the tangent line to the curve r equals 1 minus 2 cosine theta when theta is equal to pi over 4. So we'll start by saying we want to find dy dx. All right, well, that's dy d theta over dx d theta. And so that's d theta of y, and then d theta of x. But y is r sine theta. So the value of r is this equation right here. So we're taking the derivative of r, which is 1 minus 2 cosine theta, and then times sine theta. So this is r sine theta, right? And then the denominator is d theta of r, which is that 1 minus 2 cosine theta again, cosine theta. So there's my r cosine theta. So it's going to result in a product rule, right? So I have this product rule going on here. I have to do two product rules. I'm going to put a big fraction bar over here. So we have the first function, 1 minus 2 cosine theta times the derivative of the second, cosine theta, plus the second function, sine theta, times the derivative of the first. The derivative is of 1 is 0, of negative 2 cosine theta is going to be positive 2 sine theta. In the denominator, another product rule. 1 minus 2 cosine theta. So the first function, the derivative of the second is negative sine theta, plus the second function, cosine theta, and the derivative of the first again is 2 sine theta. Okay. So now, I wouldn't say it's really worth it to simplify because we want to find dy dx when theta is equal to pi over 4. So in other words, now we want dy dx at this theta equals pi over 4 value. So instead of, maybe doing a lot of simplifying here, we'll just start to plug in pi over 4 into each theta. So here's what we have. Let's start with that numerator there. So let's see, we have plugging theta into each of these. We're going to have 1 minus 2 cosine of pi over 4 times cosine of pi over 4 plus, here we might want to simplify because we're just going to get 2 sine squared theta. So we'll get 2 sine of pi over 4 squared. On the bottom, I have 1 minus 2 cosine of pi over 4 times negative sine of pi over 4, and then plus 2 times sine of pi over 4 cosine of pi over 4. And now we'll evaluate these, right? And then simplify and see what we get here. I've made some space here. So thankfully each one of these is rad 2 over 2. Both cosine of pi over 4 and sine of pi over 4 is the square root of 2 over 2. So what do we have? 1 minus 2 times rad 2 over 2 times rad 2 over 2 plus 2 times rad 2 over 2 squared all over 1 minus 2 times rad 2 over 2 times negative rad 2 over 2 plus 2 times rad 2 over 2 times rad 2 over 2. Woo! All right, let's see what happens. So these 2's here, they cancel. And let's see, rad 2 over 2 squared, that's 2 over 4, which is 1/2. So this becomes 1/2. And the same thing happens here. This is 1/2. So 2 times 1/2 is just 1. So each of these is going to become a 1. And then let's distribute here and here as well. So we have rad 2 over 2 minus, all right, we're multiplying rad 2 over 1 times rad 2 over 2. That's 2 over 2. So that's just 1. So negative 1. Then we said this was plus 1. We get negative rad 2 over 2. The negative and the negative become a positive. So that's plus 1 plus 1. Okay. Well, negative 1 plus 1 cancels. And so what are we at here? We have rad 2 over 2 over negative rad 2 over 2 plus 2. So let's clear fractions. We'll multiply the top and bottom by 2. So we get rad 2 over negative rad 2 plus 4. All right, that is our slope at the angle pi over 4. And now, as a follow-up question to the previous one, we want to find an equation of the tangent line to the curve r equals 1 minus 2 cosine theta when theta equals pi over 4. So here is the polar curve graphed, and I've actually also constructed the tangent line as well at the angle pi over 4. So pi over 4 is right here, and it turns out that that must have been a negative directed distance because the point of tangency is over here, opposite to pi over 4. So that's the point of tangency, and we found the slope of that tangent line already. So we found already in the previous part dy dx at theta equals pi over 4 was equal to that 2 over, I'll write it as 4 minus radical 2. So this is my slope, and what I also need is a point. So I need x and y. But x, remember, is equal to r cosine theta. And r is 1 minus 2 cosine theta times cosine theta. So what we need is we need to plug pi over 4 in to get out the value of x, and then we'll need to do the same thing for y. So we have 1 minus 2 cosine of pi over 4 times cosine of pi over 4. So 1 minus 2 times rad 2 over 2 times rad 2 over 2. So here, if I go ahead and distribute in, I'm going to end up with radical 2 over 2 and then minus 1. So that's the x coordinate, and then we'll do the same thing with y. Y is r times sine theta, but r was 1 minus 2 cosine theta times sine theta. So we get 1 minus 2 cosine of pi over 4, sine of pi over 4. And we're actually going to get the exact same answer because of the fact that cosine and sine of pi over 4 are both rad 2 over 2. So here, when we distribute, again, it's the exact same value. We get radical 2 over 2 minus 1. So my point My xy is rad 2 over 2 minus 1, rad 2 over 2 minus 1. So we have our m, we have our x1, y1, and we'll plug it into point slope form of a line to finish out this problem. So we have y minus y1, rad 2 over 2 minus 1, equals slope 2 over 4 minus radical 2 times the quantity x minus x1. And we'll need to keep that x1, y1 in parentheses because the negative for each would distribute. And so we'll leave our answer like this. This is an equation of this tangent line when theta is equal to pi over 4.